Welcome to Almost Here, Round the Corner Future Technology podcast with Richard Jacobs. Future technologies poised to transform our lives for better or worse are the focus of this podcast. Almost here means these technologies are now here and starting to be used, or just around the corner, from Bitcoin to artificial intelligence, 3D printing, blockchain, virtual reality, and more. Hi, this is Richard Jacobs with Future Tech Podcast, Round the Corner, Almost Here Technology. And today I'm working with Arman Zaribafiyan. I hope I pronounced your last name right, but how do you pronounce your last name, sir?
Hi, Richard. Yes, it was pretty close. I know that it's a hard last name.
Maybe we'll just call you Z, Arman Z. But,
too.
All right. Yeah, the company is onequbit.com. The number one, the letter Q, BIT.com.
Exactly.
How you doing, Arman?
Pretty good. Pretty good. Thanks. I'm happy, and thanks a lot for inviting me.
Yeah, now the real test. Let's see if I can describe briefly what OneQubit does, and then I'm sure you'll make it better. But according to their website, OneQubit produces development kits, online platforms, and applications that make the power of quantum computers available to solve problems that are well suited to quantum computation. But Arman, if you can expand and just give like a layman's view of what you guys do, that'll be helpful.
Yeah, definitely. So, Richard, we believe that quantum technology will form the next pillar of computational progress. We've seen mechanical systems evolving to vacuum tubes, to transistors, to integrated circuits, and then we've seen this progress. And now we are getting into the realm of quantum mechanics and quantum technology.
Wow.
And it's not different in that sense that we have seen the basically realm of computing being revolutionized before, but we also know that this will be a revolution unlike any previous computing design, because basically we are getting into a new paradigm of computation that's going to enable us to redefine and revisit the intractable problems with the previous paradigms of computation. So basically, our mission at OneQubit is to apply these breakthroughs in computation to fields like optimization science, machine intelligence, through a widely accessible quantum-ready software platform.
I mean, first of all, being a layperson, I didn't even know that quantum computing was real or here. Are there such things now in existence as quantum computers, and do they work?
Yes, that's a very good question. I think what we are very excited about, Richard, is that many companies and basically many researchers from academia are getting together in a collaborative ecosystem, pushing this industry forward by both looking at improving the hardware and software around it. We have groups at Google, at IBM, at Microsoft, at eWave Systems in Vancouver, looking into building a scalable hardware, and we have similar groups to OneQubit looking at basically using this hardware for interesting applications, developing software to make these technologies more accessible. So I would say yes, the ball has started to roll, and many important and big companies are interested and invested in this industry to realize this technology.
All right, so let's back up a little bit. So what is a quantum computer, and how does it work and function differently from a traditional integrated circuit transistor-based computer that we use today?
That's a great question, Richard. So first, I think if we want to get to quantum computing, the very first fundamental point is flexibility to acknowledge different paradigms of computation. So now, quantum computing is based on quantum physics. And quantum physics is basically the principle that was the physical principles first observed in subatomic particles. So now we observe that there are certain particles that exhibit a different type of behavior and a different type of physics rules in that work. Now, what we realized, like almost 30 years ago, with scientists like Feynman, they found that you can actually harness these weird behaviors, these new physics that exist there, in order to basically do useful things with it, to do computation, and they basically figured out that this is a computational resource. So they defined quantum computers. The fundamental, basically, the building block of a quantum computer is something called a qubit, which is a quantum bit. And it's very similar analog to basically the building block of classical computers, which are bits of information. Now, with the difference that this qubit follows the rules of quantum mechanics. It exhibits those weird, basically, behaviors. And the good thing is that we can harness that and use it.
Well, let's give listeners, what are some of the weird quantum effects that people have seen in the lab or in nature, and the strange stuff that you've seen that's harnessable? What's an example?
Very interesting question. So I think the most fundamental behavior is called superposition. So now that is the main difference between a qubit and a classical bit. Classical bits can only be zeros and ones, 0 voltage, 5 volt. They can have these two values at one specific point of time. Whereas qubits, quantum bits, can be in a superposition of these two values. They can be 0 and 1 at the same time. And this enables them to find easier ways to explore a complex search space of basically a binary search space or even higher dimension. So this is the most fundamental difference between qubits and classical bits that basically enables other computational resources like quantum tunneling, like entanglement, that are basically considered as computational resources for a quantum computer to solve complex problems more efficiently.
So we can, I don't know if this is a good example, but we could look at a bit as on or off or yes or no. And you're saying quantum computing allows you to have several kinds of maybes in addition to yes and no. Is that a fair example, or is that kind of too far afield?
No, that's a fair example. So the nice thing is that a qubit can exist in can have the superposition of these two, be yes and no at the same time, and then this allows the qubit to be able to consider all the options to the question that you are asking in a more efficient way, and then be able to find the right combination of answers to your question.
So let's say, all right. So if a bit can only be, let's say, on or off, it can only be in two states, a 0 or 1. A qubit, in comparison, could be in how many states versus a bit?
So it can be in any combination of that 0 or 1. The good thing is that in order to basically represent a huge space of options, if you want to represent those with classical bits, you need to basically have a much larger number of classical bits to be able to explore that big space. Whereas with quantum bits, you are able to consider all of the options with fewer resources. And these resources are empowered to basically explore a larger space. And this enables you to basically explore the space of solutions to your problem much faster. I can refer to a simple problem. Let's talk about light bulbs and switches. So let's say you are looking at a combination of basically light bulbs to basically turn the lights on in a room. So now if you have one light bulb, it's easy. It's either turning it on or off. If you have two light bulbs, then you have 4 possibilities. If you have 10 light bulbs, you have more than 1,000 possibilities. And then you can feel this exponential growth, this combinatorial explosion of the choices that you have when it comes to turning on the light bulb. So now this exponential space gets bigger and bigger, and it becomes harder and harder for a classical computer to explore. Now,
okay, so let's say if with a bit, again, it could be, let's say a bit could be in 2 states. Quantum computing, let's say, could be in 8 states. But if you have a system where, let's say, it could be in 10 states, quantum computing could be in 1,000, let's say, as an example multiple, not that it's exact. But.
So I would represent it in a different way. So let's say we have 1,000 choices. If you want to explore the best possible choice among these 1,000 choices, with a classical approach, you kind of have to go through each of them one by one and try to see which one is the most desirable one. Whereas with the quantum computer, you can explore all those 1,000 possibilities at once and basically understand which one is the best option for you. Because your qubits live in a superposition, this enables you to have insight about all of those different choices or combinations that exist instantaneously. So this is basically is coming out of superposition, and what makes quantum computers much more powerful in exploring different choices.
That's amazing. Okay, so is there any limit to this? Let's say, in cryptography, some cryptography is based on factoring enormous numbers and finding the prime factors. And I don't know how many combinations there could be, but, do you know, and how fast could a quantum computer solve a problem where you have to factor like a 256 bit number?
Yeah, so that's a very interesting question. The first application of quantum computers that comes to mind is basically deciphering the crypto system and the factoring application. This is based on the Shor's algorithm that was designed assuming a quantum computer device. What is important to basically understand is that, yes, quantum computers have applications in basically factoring hard numbers, which is the factoring large numbers, which is the principle of many crypto systems. However, we also have a lot of active research on post-quantum crypto systems, which are supposed to design new cryptography methods that now makes your system secure against a quantum computer.
I'll ask you about that, but yeah, what I'll do is ask you about, they're called quantum resistant systems, right?
Yes, they have many names, yeah.
Okay. But let's talk first about how would a quantum computer handle factoring a huge number, let's say, versus a traditional computer, and how much faster could it possibly do it?
Yeah, so a classical computer, let me start with the fundamental of the crypto system. So the classical crypto systems work based on the fact that solving some problems are extremely hard for classical computers. And as a very good example that we just mentioned, factoring is exactly one of those problems. So now, Shor's algorithm uses the same principles of quantum computing that we talked about, specifically the quantum Fourier transform, in order to solve the factoring problem in polynomial time. So now, this was a problem that was exponentially expensive and hard for a classical computer to be solved. Now, we are making it orders and orders of magnitude faster on a quantum computer using the Shor's algorithm. So now,
what's an example of the scale? Like, let's say a factoring problem would take a computer 1,000 years to solve. You know, how fast could a quantum computer theoretically do it? Or if you have better numbers, you know, let's go with those. Just, again, ballpark. I know it's not tied to any specific application, but just a ballpark, how much faster could a quantum computer solve a problem like that? Like, how long would it take a traditional one, and how long would it take a quantum one?
Okay, so instead of talking about time, let me talk about the choices that we have. So for a classical computer, the runtime scales exponentially in the number of bits that you use to represent the number that you want to factor. So let's say if the number has if the number is represented with 100 bits, then the runtime of the classical algorithm is going to scale with 2 to the power of 100. When you look at the classical algorithm, the scaling is polynomial in basically the number of those bits. We are talking about like 100 or 100 squared or something like that. So now you can compare how different these two numbers are compared to each other. That's how the scaling of the runtime of a classical computer versus a quantum computer works.
Okay. All right. So it's all right. What are some other examples of problems that quantum computers would be better and faster at solving, and what are some examples of ones where there is no edge in having a quantum computer?
So that's an interesting question for us, especially because we are very interested in exploring applications of quantum computing. We are engaged in professional services with many industries to explore interesting problems and applications that are amenable to quantum technology. I would say optimization and machine intelligence, and in general, the notion of NP-hard problems or complex problems for classical computers are the best ones that are basically the best candidates to be explored with quantum computers. Now, optimization is everywhere. Is in logistics, is in like pharmaceutical companies, big manufacturers, finance, and energy industries. Like wherever you look at, engineering is about optimization. And there are certain types of optimization problems that are extremely hard for classical computers to handle, and those are the best candidates that basically quantum computing can start to explore and answer.
So let's say like UPS or FedEx.
Mm-hmm.
A possible use would be, the computer looks at all the trucks and planes and deliveries that are out every second, and it dynamically calculates the most efficient way to deliver all the packages in the shortest amount of time. Would that be a possible use of quantum computing where it would be a real sweet spot for it?
Exactly. We are exploring applications similar to that, like this is based on this traveling salesman problem and trying to find the best possible path to distribute. In general, as I said, the optimization exists everywhere, especially in logistic problems like the example that you had. And yes, a quantum computer will be able to basically go through the options possible for problems like that and be able to respond faster and with a more accurate and faster solution to this problem.
Okay. And what's an example of a complex problem that quantum computing would have no benefit over traditional computing?
That's a very good question. So in general, investigating what problem is a good candidate to benefit from potential quantum computing is very case dependent, and it's very hard to generalize. But for example, with the available computing devices, problems that involve discrete choices, problems that involve many decision making are much closer to be able to benefit from quantum computing than problems with continuous variables, continuous choices. And this is basically the very first thing that comes to mind when we want to compare where quantum computing is very powerful and when classical computers are powerful.
Okay. And I guess, why even worry about that? Why not just worry about as many situations as possible where it could apply? So maybe it's a silly question, but okay. So can I go and buy a quantum computer from a store? Or, if I'm Google, do I have one sitting in my labs that's actually working and computing? I mean, where in reality are we with these computers? Do they exist and are they running? And how powerful are they? And are they working on problems right now? Like, what's the state of the industry?
Mm-hmm. Interesting question. So many big companies are invested in manufacturing quantum hardware, from Google, IBM, to Vancouver-based D-Base Systems. They are building devices. Some of these companies are focused on commercial hardware. Some of them are still working in lab to basically improve their hardware. And I think it's a new industry, but a very fast-growing one. So when I will tell you a story. When I joined Qubit 4 years ago, we had access to a chip with 128 qubits. Now 4 years have passed, and now we have access to. We are talking about a chip that has 2,048 qubits. So this is like 16 times more qubits in 4 years. Not that it's only the number of qubits that matters, but I just said that to show how fast the industry is growing. So yes, it's a new industry, but it's growing very fast with Google working on different paradigms of hardware, with IBM, with Microsoft, looking at basically both developing software and hardware. I think many big companies are invested in the industry, and it's growing very fast, and we are very excited about its future.
Okay. So the software that One Qubit creates, what kind of applications have you made, or what are you making, and what do you hope it'll do? What kind of interfaces are you making with quantum computers that people will use?
That's great. So let me answer this question in a couple of levels. So our goal is to be able to transform a complicated technology into an accessible technology to industry. And we basically do whatever it is in our power to make that possible. We are basically focusing on different types of applications. We explore these applications with different industries, and then we fundamentally look at how we can generalize these tools and how we can make it more accessible. And whenever we come up with new tools, we implement them in our software development kit that enables developers to basically interface and interact with these devices much easier without really worrying about the intricacies and complications underneath. One important point about our software development kit is that it is hardware agnostic. This is very important for us because this is a fast-growing industry, and many different companies are looking at different realizations and different paradigms of these computers. What we want to make sure is that an end user or an industry, they don't need to worry about what paradigm they need to choose, what hardware they need to work with. What they need to know is they need to program, basically, they need to understand their problem and then be able to program it once on these hardware agnostic software development kits. So it basically enables the user not to worry about the different paradigms, different platforms, different interfaces, and the basically details and intricacies of using these devices.
So what do you guys have one or more quantum computers, at your offices that you're sitting there programming?
We collaborate with different manufacturers, and we have basically access to the hardware that they build. We collaborate in that way, basically.
What does the quantum computer look like? Is it tiny? Is it huge? Does it have all kinds of, parts to it, or does it look innocent and small, like nothing special?
I like that comment. It looks very innocent and small. So let me describe it in this way. There are many groups who are interested in developing hardware, but most of these groups are interested in superconducting qubits, for example. These superconducting qubits are built with basically chips that are very, very similar to the basically classical chips that we have. They are fabricated on like silicon-like wafers, and they are very similar in that sense. In fact, the devices that we are talking about right now are like a qubit in can be basically is in the order of nanometers or that small basically. But in order to make sure, like quantum computer is a very sensitive and fragile device. These qubits are very sensitive to noise and environment. So in order to make sure that that tiny chip is working properly and it is exhibiting the kind of behaviors that we expect from it, we have to protect it. Now, the devices that are used to protect this chip can be big. So there's a lot of shielding involved, and it has to live in a fridge that basically, I think its temperature is the lowest temperature possible that you can find on Earth in order of millikelvins, close to absolute zero. So it has to live in an environment like that to be protected and to basically exhibit to basically work in the way that we like it to work. So now those devices that are surrounding it in order to create that environment for it are big, but the chip itself is a very small chip, like the other superconducting chips that you might have seen.
So like a silly example could be a giant freezer, a giant armored freezer, and inside in the center you'd have like one P that would represent the computer, or even smaller than that.
Yes, exactly. Yeah.
Huh.
It's actually one of the hardware that is manufactured by D-Wave, for example, lives in a black box that I think is 2 meters by 2 meters. But the actual chip that has all the qubits on it is maybe 1 centimeter to 1 centimeter. That is small.
Okay. Yeah, and a couple questions about the physical structure of the qubit itself. What is it manipulating? A photon or electrons, or what is it made of? I mean, how does it work? If you can describe it.
I'm glad you asked that question, Richard. So there are many different ways to build a qubit. And in fact, many, as I mentioned before, many big companies are looking at different types of qubits. There are superconducting qubits that are built out of basically superconducting circuits, are built based on something called Josephson junctions, and these are basically tiny circuits. And there are quantum computers based on photons. They are quantum computers that work with trapped ions, with fault atoms. There are different ways to build a qubit. And each of them has their own strengths and weaknesses and applications.
Huh. And what, okay, so I guess for the sake of the interview, what's the, to you, what's the most amazing way that a qubit is constructed? The one that just blows you away, and how is it constructed?
I think I'm very excited about superconducting qubits because in general they are first of all, we can use the previous experience that we learned about fabricating classical computers in order to make them better, control them better. But on the other hand, I'm very fascinated and excited about topological quantum computers that, for example, groups at Microsoft are looking into building them.
Okay, so what's an example? Like, what is it about it that fascinates you so much?
So the interesting thing is that it was shown that if you create these abstract things called quasi-particles that are called anions, if you build these, if you have a way of building them, then by braiding them, you can actually do computation. And it is actually shown that this type of implementation and this type of computation is very resilient to noise, and it's very well protected against noise, which is a very important advantage in building qubits. And just the fact that you can take these particles, braid them, and this does computation for you is really fascinating. Now, this is a very abstract and complicated subject, but I'm really fascinated by that research as well.
Okay. Do you think that, I mean, what's going to be happening in the next 2 to 5 years, maybe 2 to 10 years? What's possible, and what do you think is fantasy in the quantum computing world?
Well, one thing that I can say for sure is that the industry is growing very fast. I told you about going from 128 qubits to 2,000 qubits in 4 years. I know that the industry is going very fast, and one thing that I really like about this industry is the ecosystem. One Qubit itself is very invested in creating a collaborative ecosystem that hardware manufacturers and software developers can work together to make this a reality. I think this ecosystem is there, and we are very excited that we contribute to it. And this is basically the recipe, I think, the recipe of success, and it's growing very fast. We will see many different realizations of these devices in the future, and I believe that the future is very bright and exciting.
Do you think that we're ever going to have, with all the shielding required and the sensitivity, do you think we'll ever have a laptop or a smartphone that's a quantum computer, or is that just never going to happen?
Well, it's hard to predict what would be the meaningful form for these computers to exist. It can be a decentralized device that everyone has in basically their laptop or their mobile phone, or it can be a centralized device that everyone can access to it and benefit from its advantage. One thing that I can say for sure is that it has many applications that will affect everyone's life. It is such a fundamental subject. It's basically a new paradigm of computation. So it helps you find new derives. It helps you basically have a more secure and less risky investment. It helps you make better batteries to store more renewable energy. I think just the fact that it has many interesting applications makes it a technology that is going to affect everyone's life. Maybe not in the form of a quantum laptop, or maybe in that form. Who knows what the future is? But what I'm trying to say that only based on understanding diverse applications of it, we can anticipate that it's going to be a very important technology for everyone.
Okay. All right. Just a couple more questions. How could a system or something be quantum resistant? What does that mean, and can you talk more about that? Because it's just it's an unusual concept.
So I believe by quantum resistance, you basically refer to post-quantum cryptography systems.
I guess, yeah, maybe I'm talking about, the Heisenberg uncertainty principle, that by measuring something, you disturb it, so therefore you can't measure it, you can't get an accurate estimate of exactly where it is or how fast it is or that kind of thing. Is there, can you use that principle to engineer systems that could not be affected positively or negatively by quantum computing?
Yeah. So in fact, I'm going to refer back to post-quantum methods and approaches. And yes, there's a lot of research on basically devising methods that are now assuming, based on the fact that you have a scalable quantum computer, how does it affect, for example, the cryptography systems, and how we can make them secure using all these quantum effects to make them secure in the presence of such a powerful computing device. So yes, I see a lot of research on this topic, and it is also a growing field.
Okay, very good. So besides getting a PhD in physics, what's a good way for listeners to learn more about quantum computing and get a grasp of it and a better understanding of it, and to find out about what one Qubit is doing and other players in the space?
That's a very good question. So we actually believe a lot in making the ecosystem and educating people and developers and facilitate working with this technology for them through the software, through our basically direct the professional services with industries, and through making the research and the tools that we have available. If you go on our website, we have a limited version of our software available through Jupyter Notebook with great details and documentation, and you can use this basically to learn more about what are the potentials of quantum computation, and you can also learn how to use these levels of software that we develop in order to access and benefit from this technology easier.
Okay, well, very good. Anything?
If you just wanted to check it out, the address is qdk.onequbit.com, and QDK stands for Quantum Development Kit, and many interesting tutorials exist on that website. In addition to that, we also make our research, fundamental and applied research, publicly available, and those publications and either white paper or scientific papers are also available through our onequbit.com website.
Okay, very good. Any other questions I should have asked you that you want to bring up?
I think one of the questions that I'm asked a lot. People ask me a lot, and I like to talk about it. Is basically where do we see one qubit in future? And I think we are we are working in a very fast-paced and growing industry, and we explore an increasing number of applications based on this new technology. And we are very excited to see the ecosystem that is built, and we are excited to see that many hardware companies as well as software companies are trying together, collaborating to make progress and improve this industry. We are very excited that we are part of it, and we really look forward to this exciting future.
Okay. Well, very good. So Arman Z, I won't say your last name because it's so difficult. It's as difficult as some of the quantum computing problems we face. Just kidding. But from one qubit, thank you for your time, and it's been an interesting interview.
Thank you. It was very interesting for me as well. Thanks a lot.
You have been listening to Almost Here, Around the Corner Future Technology podcast with Richard Jacobs. Subscribe to this podcast, post a review to discover more future technologies that are poised to transform our lives for better or worse, such as Bitcoin, artificial intelligence, 3D printing, blockchain, virtual reality, and more.
Have a more secure and less risky investment. It helps you make better batteries to store more renewable energy. I think just the fact that it has many interesting applications makes it a technology that is going to affect everyone's life. Maybe not in the form of a quantum laptop, or maybe in that form. Who knows what the future is? But what I'm trying to say that only based on understanding the diverse applications of it, we can anticipate that it's going to be a very important technology for everyone.
Okay. All right. Just a couple more questions. How can a system or something be quantum resistant? What does that mean, and can you talk more about that? Because it's just it's an unusual concept.
So I believe by quantum resistance, you basically refer to post-quantum cryptography systems.
I guess, yeah, maybe I'm talking about, the Heisenberg uncertainty principle, that by measuring something, you disturb it, so therefore you can't measure it, you can't get an accurate estimate of exactly where it is or how fast it is or that kind of thing. Is there, can you use that principle to engineer systems that could not be affected positively or negatively by quantum computing?
Yeah. So, in fact, I'm going to refer back to post-quantum methods and approaches. And yes, there's a lot of research on basically devising methods that are now assuming, based on the fact that you have a scalable quantum computer, how does it affect, for example, the cryptography systems, and how we can make them secure using all these quantum effects to make them secure in the presence of such a powerful computing device. So yes, I see a lot of research on this topic, and it is also a growing field.
Okay, very good. So besides getting a PhD in physics, what's a good way for listeners to learn more about quantum computing and get a grasp of it and a better understanding of it, and to find out about what one qubit is doing and other players in the space?
That's a very good question. So we actually believe a lot in making the ecosystem and educating people and developers and facilitate working with this technology for them through the software, through our basically direct the professional services with industries, and through making the research and the tools that we have available. If you go on our website, we have a limited version of our software available through Jupyter Notebook with great details and documentation, and you can use this basically to learn more about what are the potentials of quantum computation, and you can also learn how to use these levels of software that we develop in order to access and benefit from this technology easier.
Okay. Well, very good. Anything?
If you just wanted to check it out, the address is qdk.onequbit.com, and QDK stands for Quantum Development Kit, and many interesting tutorials exist on that website. In addition to that, we also make our research, fundamental and applied research, publicly available, and those publications and either white paper or scientific papers are also available through our onequbit.com website.
Okay, very good. Any other questions I should have asked you that you want to bring up?
I think one of the questions that I'm asked a lot, people ask me a lot, and I like to talk about it, is basically, where do we see one qubit in future? And I think we are we are working in a very fast-paced and growing industry, and we explore an increasing number of applications based on this new technology. And we are very excited to see the ecosystem that is built, and we are excited to see that many hardware companies as well as software companies are trying together, collaborating to make progress and improve this industry. We are very excited that we are part of it, and we really look forward to this exciting future.
Okay. Well, very good. So Arman Z, I won't say your last name because it's so difficult. It's as difficult as some of the quantum computing problems we face. Just kidding. But from One Qubit, I thank you for your time, and it's been an interesting interview.
Well, thank you. It was very interesting for me as well. Thanks a lot.
You have been listening to Almost Here, Around the Corner Future Technology podcast with Richard Jacobs. Subscribe to this podcast, both to review, to discover more future technologies that are poised to transform our lives for better or worse, such as Bitcoin, artificial intelligence, 3D printing, blockchain, virtual reality, and more.
Many hardware companies as well as software companies are trying together, collaborating to make progress and improve this industry. We are very excited that we are part of it, and we really look forward to this exciting future.
Okay. Well, very good. So Arman Z, I won't say your last name because it's so difficult. It's as difficult as some of the quantum computing problems we face. Just kidding. But from one Qubit, I thank you for your time, and it's been an interesting interview.
Thank you. It was very interesting for me as well. Thanks a lot.
You have been listening to Almost Here, Around the Corner Future Technology podcast with Richard Jacobs. Subscribe to this podcast, post a review to discover more future technologies that are poised to transform our lives for better or worse, such as Bitcoin, artificial intelligence, 3D printing, blockchain, virtual reality, and more. Worse, such as Bitcoin, artificial intelligence, 3D printing, blockchain, virtual reality, and more.